All right, so in a previous slide or section, just the one before, I was talking about buffers in a very qualitative manner, right? And I was explaining them in terms of Le Chatelier's principle. But you can put some numbers on this stuff. So that's what this thing is, the Henderson HBalch equation. My guess is somewhere along the line you're going to encounter this again. So we're going to have a look at this in a little bit of detail. Now, the equation itself is there, okay? And basically what it's allowing you to do is calculate the pH of a solution for a particular acid if you know what the concentration of the acid and its conjugate base are. Now, more on that in a minute. I just want to also very quickly explain how you would derive the Henderson HBalch equation. So, by the way, you don't need to know how to. I'm just explaining it for those of you who are to those of you who are interested. So, if you remember the sort of general format for a weak acid and its dissociation in water, it's something like this. And of course, there's a dissociation constant that can be written for that particular equilibrium there. And of course, it's products over reactants. So there's the products, A- and H3O+, there they are, over the reactant, which in this case is HA. And remember, you don't put the water in because water's a constant. Now, what we're going to do is we're actually going to rearrange this equation. What we're interested in really is getting this H3O+ on the left-hand side of the equation. So that's pretty easy to do. There it is there. Now, the reason we want to do that is because we're then going to take the negative log to base 10 of both sides, which of course we can do. And there's the negative log of that, negative log of that, negative log of that. Well, the negative log to base 10 of the H3O+ concentration is the pH. There it is. The negative log to base 10 of the Ka is obviously the pKa, and you're left with this value here. Now, can you see that this was a minus and now it's a plus? And the reason for this is these guys are being flipped upside down. So you end up with this equation here, the Henderson HBalch equation. And I'll give you some examples in a moment of how you can use it. There's my little summary of how you can use it. You can calculate the pH of a buffer. If you know what the pKa of the acid is and the concentrations of A- and HA, or you can calculate the relative amounts of A- and HA if you know the pH and the pKa. ... Obviously, I'm going to give you some examples. So here's a question here, straight out of your textbook, where they're telling you what the pH is there at 7.4, and they're then saying, okay, in this problem here, they've got this is a buffer solution here with bicarbonate, and we've got a concentration here and a concentration here. Now this is the HA, this is the A-, right? And they can calculate the pH directly from this equation here. So they know what the pKa is. So what they're going to do now is they're going to plug the numbers in. So we're trying to find the pH of this particular buffer system. We know what the concentration is of the, let's do the A- first. It's there, right? So it's the A- over the HA. Okay, the A- is that value, plug it in. The HA is that value, plug it in. And the pKa, where is it? Oh, they haven't given it to you in the question there, but the pKa is 6.4. So they plug that value in there and they can then calculate the pH, and it's approximately correct. Actually, this system's much more complicated than that, which is why you would expect it to be approximately correct. By the way, you're going to do this in your prac in week 9. You're going to play around with this particular buffer system here. Just be aware that this stuff is called carbonic acid, and this stuff is called hydrogen carbonate ion, which I never call it. Most people don't, because they use the old school term, which is bicarbonate. I've got that written down there in case you get confused. Anyway, bottom line is this. You can use the Henderson HBalch equation to calculate the pH of a buffer system if you know the concentration of an acid, its conjugate base, and the pKa of the acid. This one's just another example. Calculate the pH of a buffer where it's got this much acetic acid and it's got this much acetate ion. Now, what you're relying on here is that you can actually recognize this is the HA there. This is the A minus here, and they don't actually give you the pKa, but they give you the Ka. So you actually have to take the negative log to base 10 of this and then plug the numbers in. So there's the equation. Oh, that's gone a bit messy there. Let's plug some numbers in here. Go down to here. pH is equal to the pKa. Well, the pKa of 1.8 by 10 to the minus 5 is 4.7. Plug it in there. And the A minus concentration, here it is here, is 0.6. The HA concentration is 0.1. Obviously 0.6 divided by 0.1 is 6, so it's a log of 6 plus 4.7. We end up with the pH being 5.48. That's the answer. So that's the pH when you have that particular buffer system there. Now, this is just a bit of an extra. You guys don't really have to know this. But I just want to point out to you that the other way you can use the Henderson HBalch equation is to actually work out how much of an acid's been ionized if you know what the pH is and you know its pKa. So in this case, we've got aspirin here. There it is there. It has a pKa of 3.5, and we know the pH is 1. So how do you do that? We use the Henderson HBalch equation. The pH is equal to the pKa, those numbers up there, as I said, plus the log of the ionized, that is the A minus, over the unionized, which is the HA. And if you plug those numbers in, then take the anti-log, you get this number here, right? So this means the amount of A minus is this much relative to what? The HA, which is 1. In other words, for all intents and purposes, there's no A minus. It's all HA. Well, what does that mean? So in your gut, aspirin is mostly in the unionized form, which actually makes it a little bit easier to get across cell membranes because they tend to be fairly fat soluble. Okay, just a couple of other things with buffers that I need you to be aware of. As I said before, basically they're going to do their job best when you've got roughly equal amounts of acid in the conjugate base. This is basically where the pH is equal to the pKa, right? How do you know that? Well, if you write the Henderson HBalch equation and you say the pH is equal to the pKa, well, that means that minus that would be 0, and then the anti-log of 0 is 1. So log to base 10 of this would be 1 over 1. Now, if you didn't understand what I meant there, don't worry about it too much. I just need you to know that basically for buffers, they're going to work best when there's equal amounts of acid in its conjugate base, and that is where the pH is basically the same as the pKa. And that is important because when you're choosing buffers, you want to choose a buffer whose pKa is roughly the same as the pH that you're trying to keep stable at that point. Buffering capacity, just so you understand the difference here between that and looking at whatever the particular pH is. Buffering capacity is determined by the actual concentration of the buffer, and so that's important. If you have something that you know is going to produce large amounts of acid, for example, you want to have a high concentration of your buffer. The relative concentrations of your acid and conjugate base are actually determining the pH, right? The amount to which a buffer will significantly do its job is dependent by the absolute concentrations. Here are these guys, not the relative amounts. So just be aware of that. Okay, that's it for that section on buffers.